started. My name is Tom Ball. I'm from Microsoft Research, and today I'm going to tell you about how over the last 2 decades, which is about the time I've been at Microsoft, we use automated theorem provers based on foundational logic and programming languages to enhance the reliability and correctness of our systems. In particular, we'll focus on the cloud today. So here's a scary diagram about complexity classes, starting with the simplest in some sense, MP completeness, for which we have the SAT problem. And we have actually, despite the problematic nature of MP equal MP, we have SAT solvers. As we go up the logic hierarchy, we have things like P-space, polynomial space, non-deterministic exponential time, semi-decidable first-order logic, and undecidable logics like first-order logic plus linear integer arithmetic. And because of this hierarchy, we have a trade-off between less expressive languages, like propositional logic at the bottom, for which we have a lot of automation, like SAT solvers, and then greater expressiveness of logic higher in the hierarchy, but we have undecidability, so we need some way of coping with that if we want to do proofs of systems in more complex classes. We have decades and decades of careful engineering and large-scale evaluation of solvers at the low level. We have algorithmic advances on decidable problems, and we have the user control of proofs through languages and language abstractions to deal with complex logics, as we'll see in the talk. So today I'm going to walk you through 3 examples. We're going to start with simple logics, relatively simple, propositional, quantified Boolean formula characterizing SAT and P-space. We're going to talk about Boolean programs and how they were used to model device drivers and do automated verification. And then we're going to pop up the hierarchy to first order with theories and how a type system was devised to incorporate both type checking and satisfiability modular theory solvers. And then we will come down the hierarchy to effectively propositional logic and a new language called Ivy that uses restrictions on the language to look at decidability. But first, let's talk about one of the biggest trends in the last 20 years, which is the reduction of hard problems to SAT or SMT. So if you have a language or you have a problem, often if you can reduce it to a SAT formula or SMT formula, there are now off-the-shelf solvers that will help you. And so if you have a propositional logic with the values true and false and Boolean variables and connectives, you know, it's only NP complete. So these days you can find many, many SAT solvers to look at the questions of satisfiability. One of the things Sridhar Majumani and I looked at 2 decades ago was, well, what if we took propositional variables and made that the type system of a C program? So imagine a C program where you get rid of all the types except for void and bool. Okay, and so you have recursion, you have a stack, but you only have a finite number of variables. You don't have a heap. So what would you think that reachability would be? Well, it turns out it's decidable. Even though you have one stack, well, actually it's only because you have one stack, reachability is decidable. So we thought, well, that's sort of interesting. If each Boolean variable represents an observation of program state, then you could do something maybe interesting using Boolean programs as the basis for program analysis. And it turns out if you're into the particulars of the language, if you have no variables, then you just have a push down, then reachability is linear. If you have a single procedure, variables but no loops, you're NP complete. If you add loops, you're in P-space. If you add procedure calls but only hierarchy, no recursion, you remain in P-space. And if you go to recursion, you're in X time. So there's a really interesting a question of which programming languages constructs you have and what the complexity of reachability is, even for the simple model. So it's been really well studied. So what we wanted to do, Sriram and I 20 years ago, was look at C programs and somehow abstract them into Boolean programs to check control-dominated properties. So over on the left here, you see a little state machine, and the state machine has 2 good states to be in. Either you're unlocked You have a lock, it's unlocked, you acquire the lock and you go into the lock state, or you release. So there's this sort of virtuous cycle of acquiring release. But if you release from a unlocked state, or you acquire from a locked state, you go to an error state. So this is what's known as a safety property. And here's a C program that has acquire and release of the spin lock, which corresponds to these rel and ack actions. And it has some other stuff too. It has pointers, it has some arithmetic, and it has a conditional. So it's not immediately clear if this C program satisfies the property. So what we did some 20 years ago now is we said, well, okay, can we automate searching for bugs in this program or finding a proof that it meets the property? So what we did was we first threw away all the data. So imagine getting rid of all the data, all the pointers, all the heap, turning every predicate into non-deterministic choice. That's what the star is. And then just keeping the state of the state machine around. So now we have a finite number of program counters, we have loops, we have the state of the state machine. It's a Boolean program because we threw away all the state. And if we do model checking on this, you know, the model checker is going to go through various states. We start in the unlocked state, we acquire a lock, we get into the lock state. Let's say we skip the if and we exit the loop and everything's happy because we acquired the lock and then we released it after exiting the loop. If on the other hand, the model checker goes inside the if, there is a path where, since the while condition of the do while loop is also non-deterministic, it can exit the loop and get to an error. So does anybody think that's a real error in the program? Raise your hand. Okay, somebody, there's one in the back. Well, let's take that path, and what we did in the SLAM project was we gave it to a theorem prover and we asked, does there exist an input now in the concrete world such that this path could execute? Well, notice that along that path there's these two variables, n packets and n packets old. N packets old is equal to n packets. If we go inside the if, we increment n packets, so the while loop actually must iterate, right? Because at the end of this loop, it's not possible to exit. So this is what happens when you abstract from a C program to a Boolean program. You get many more traces, and you don't want to show an infeasible trace to the programmer. So what we did, we used a theorem prover, and we found a predicate that basically captured the reason for why that path is infeasible or unexecutable, and not surprisingly, that packet, that predicate is the predicate n packets old equal to n packets. And in the Boolean program, we just have a single bit, and the bit tracks the state of that predicate. So the assignment statement, n packets old gets the value of n packets, makes the bit true. N packets plus plus is a little bit more interesting. If the predicate was true before the assignment, it's definitely false after. If it was false before, well, we don't know after. So there's still non-determinism. And then we refine the predicate in the while to the negation of B. Right. Now, if we eliminate everything else again, get rid of all the pointers, and do our model checking, when we're doing the model checking, we're tracking not only the state of the state machine, but of the bit B. So along the path that was a good path, B was true, and so the loop actually must exit. It has no choice. And when we get to the release spin lock inside the if, then we negate, then B becomes definitely false, and so the loop must iterate. And now we actually reach a fixed point, and that's because we've automatically discovered a loop invariant. That is, the state of the state machine is locked if and only if n packets old equal n packets. Okay, so this is a form of automated verification where we're discovering interesting predicates by doing this model checking of a Boolean program, finding these paths, checking if they're infeasible or not, using an automated theorem prover 2 in the C program, and then doing some refinement. So this is something we did 20 years ago, and it was the idea of reducing a hard problem, in fact, an undecidable problem, of safety properties of C programs to a simpler problem of model checking of Boolean programs. And so this is actually a semi-algorithm because it can iterate forever, finding predicates and never finding a proof, but often it will terminate, and it will terminate by finding bugs, which is really what we were after here. And so in 99, we started this project, and then as the saying goes, luck favors the prepared. In 2001, NIMDA and Code Red Worms took down a lot of Windows PCs in the world, and there was this thing called the Windows Security Push and the Trustworthy Computing Initiative. The security definition lifecycle started by Bill Gates. They founded a new team called Windows Driver Quality in 2002, and Sriram and I helped hire people into that team, and we took SLAM to production and made a tool called Static Driver Verifier for checking these sort of properties, these safety properties, control-dominated safety properties in device drivers, in the C code of these programs that come from third parties, these programs that interface the operating system to the hardware. Since 2004, automated verification of this sort, which takes a C program and some simple properties, has seen a great explosion, thanks in no small part to the rise of these automated theorem provers like Z3, which was a project started in MSR in 2006 and going strong till this day. As a result of Z3, we had a number of engines that took over from SLAM that made different trade-offs. They didn't translate to Boolean programs. They translated C programs directly into formulas and used SAT solvers and SMT solvers to solve them. So there's been a huge body of work really on the problem of how do you reduce the problem of checking with a C program with pointers and heaps and floats and ints to how do you reduce that problem to a problem of satisfiability or validity checking of formulas and leveraging these SMT solvers. So Z3, if you haven't heard about it, is this state-of-the-art SMT solver from Microsoft Research. It targets mainly applications in software engineering, testing, program analysis, verification. It was started by Leonardo de Mora and Nikolai Briona. Christoph Wintersteiger from MSR Cambridge joined as well. And now it's an open source project. It's available on GitHub under the MIT license. We have contributors from within Microsoft as well as outside, and it's much more than an SMT solver these days. It has optimization, MaxSat, it has a horn clause solver, it has interpolation. So if you're interested in using logical solvers, I definitely recommend Z3 to you. It has various language bindings, Java, Python, C. I think those are the main ones. So let me just tell you quickly about some of the other uses of Z3 of this reduction of sort of hard problems to logic. One of the big ones that's seen a lot of use over the last, say, a decade or so is automated test generation. So given a program in your favorite programming language, here it happens to be C#, we want to search for bugs. And here we're not trying to get a proof like we did with SLAM, but enumerating paths through the code and encoding the semantics of the program path in the language of SMT. So here we have a C# program, and we're asking the question, does there exist a value for integer x that will cause us to throw an exception? So you can puzzle over that. You see bit shifts, you see logical operations, arithmetic operations. Why not let a SAT SMT solver make that job easier for you? There are many tools that will now translate paths in programming languages, encode the semantics in SMT, pass it to something like Z3, get an answer back. So get an explicit model. In this case, the answer is SAT. The encoding of this path was done using the bit vector theory and nothing more, since there was no heap really in this example. And Z3 gives back a value that if you compile that C# program and give it that value, it will throw an exception. So obviously this is very valuable, and we have a whole service now called the Microsoft Security Risk Detection Service that we make available to third parties, where they can send us executables, and we will essentially, x86, we will do this generation of bit vector formulas automatically on x86 to find essentially inputs of death, things that, byte streams, if you will, to file read operations that would cause null pointer dereferences or worse. And so there's a huge amount of work here on how do you reduce programs and do path exploration to find these inputs that cause failure. Another thing that's happened in the last 4 years is really neat, driven by Nikolai Bjorna, is what's called network verification. So imagine your data center, and you're building out your data center. Not only are you putting an operating system on it, you're configuring all the routers, all the access control lists. So the correct operation of your data center is a function not of just the programs running on it, but all the router configurations. So often these things have very, very low-level details about IP addresses and which routes are to be allowed and which are to be denied. So we've created, for pretty much all the different routers we use in Azure, compilation from these routing tables, configuration tables, into bit vectors. So you can basically say for a source IP address in this range and a destination IP address in this range for protocol 6, whichever one that is, we want to allow traffic, right? And this is just, this is automatically, these formulas are automatically the result of a compiler that takes the configuration table and gives us a bit vector. We have a combining semantics, which basically takes those core formulas and does the sort of obvious thing. And then we actually have contracts and policies on the left-hand side. So given this data center, there are certain services we have in it that should not be accessible from VMs, user VMs, right? So we have a whole set of policies and configurations. And the question is, does the program meet the spec? So it's very much like what we saw with SLAM, but instead of C programs as the object of inspection, we're looking at the configuration tables. And so every day, in fact about every 15 minutes, this tool called SecGuru runs on all the configuration tables in all of Azure, all around the world. It does, this is an old slide, so it's probably more like 100,000 ACL checks, but it's finding errors that are introduced by humans, generally when we're doing build out. So when we're building out a new data center or adding new capacity, there can be errors in these tables. Sometimes the tables get very large and people want to compact them. So when you're doing when you're doing some refactoring, you'd like to know that the contracts are being maintained. So here, there's a very nice and actually very precise. There's no abstraction. There's the compilation of these configuration tables to bit vectors retains fairly precise semantics, and we get automated checking. And this can be done in a number of modes. It can be done inside while we're building out. It can be done live as well to generate audits of the existing data centers. If you want to see more about that and sort of do your own style of access control, we actually have an open source firewall checker that's built on .NET Core, that's done by Andrew Hewler. So this essentially encodes a lot of the ideas we have in SecGuru, and you can see that under the Z-Theory Prover at github.com. So you can see examples of how we take a network configuration and go to Z3 for automated checking. Okay, so that was a really, really fast tour of essentially reducing problems in a variety of languages. The problem of checking C programs, the problem of finding inputs of def in C# and checking configuration files, by essentially compiling those problems down to satisfiability in SMT. So what I'd like to do next is consider a language that actually elevates and brings SMT up into the type system. So what if you had a type system where you had much more expressive capability? You could express arithmetic facts over your types. So you could use integer linear arithmetic or nonlinear over the reals at a higher level of abstraction. What would that look like? And this is essentially the F-star programming language. How many people here know F-star or heard of it? Okay, great. So F-star is essentially an ML-like language. Its base is F#, but the type system is much, much richer. You have a very expressive type system with dependent types, refinement types. You have effects. monadic effects, and it's supported by a weakest precondition calculus, which is essentially how you take F star statements and then reduce them with the specification to the input language of a SMT solver. So the F star type checker, unlike the SLAM project, gives the user much more control. You have not only the specifications, you can write loop invariants, pre and post conditions, and there's a whole tactic language, because often when you're working with very expressive logics, you need to control the proof at a much finer level of detail. So if people are familiar with interactive proof assistants like Coq or Isabelle or things like that, you actually have control meta-programming over the terms of your language and proof to organize your proof better, and F star has that as well. So what's been going on in F star for the last 3 years really is to take the F star tool chain and climb a big mountain, and they call it Project Everest. And the whole idea is to use F star and Anger to build a substantial artifact, prove it correct, but also extract code that is high performance. And the mountain they want to climb here is HTTPS, so there's quite a large ecosystem. They want to provide, in this project, strong verified security, so not just safety properties, memory safety, but cryptographic security, confidentiality, some form of denial of certain types of attacks. There's a huge set of modules here. At the low level, network buffers above these cryptographic algorithms, TLS, which is SSL, if it gives you the S in HTTPS, and then at the higher level, a lot of the messaging protocols. So carving out this module, looking at how much of this can be verified, but with an idea towards extracting code that C code, as a matter of fact, that will be deployed in real-world scenarios. So not just doing a proof of concept for a paper, but actually being able to generate code that passes code inspection, validation tests, and has the performance required to be incorporated in a modern-day web server. Clearly, this is relying on the toolchain, F star Z3, and there's been a lot of additions to both tools to support this endeavor, and really grow a team that's in three countries: the U.S., the U.K., and also France. There's probably, I think we also have India. We have a whole team, distributed team, that is building not just the tool chain, but the verified components that are using the tool chain. So here's a very quick overview of the code that's being built. At the top is MITLS. That has been led by Cedric Fournet and others in Cambridge, where you have a protocol. You need to ensure the confidentiality and integrity of the channels and the transmission between parties. There's a lot to say about that, but I'm not going to talk about that today. There's a question of all the messages, all the message types that have to be exchanged, and we have a whole, Tahina, Ramanandra, and others have created a whole domain-specific language for verifying parsers and enforcing very interesting properties there. The thing that I'll talk about today is the effort called Evercrypt. And so this is a module to provide industry standard cryptographic algorithms that are widely used, but to provide, again, fully verified and performant versions of these. Because if you don't know, there's a lot of hand-coded assembly and C for these crypto algorithms that in practice has lots of bugs. So what's happening in F star is that for a given polynomial or a given crypto property, they're going to write essentially pure math in F star, the mathematical truth. That is, they're translating the specification of the particular polynomial into F star, and that can be compiled and can be subject to tests at the very highest level. So this would be somebody, the mathematician, encoding encoding, what is the meaning of a particular polynomial. From that, the developers have created a pseudocode to actually realize a more efficient implementation of that, but that pseudocode is still left a lot of binding decisions, like bit width, how you're going to pack and unpack things, has left that unspecified at this point. So that's F star code, and there's a refinement proof that pseudocode implements the particular polynomial. And then there are two ways to actually implement to refine that pseudocode. One is done by Chris Hobwitzel and team, and this is a assembly-like language that's encoded into F star and is shown to refine the pseudocode. And then there's also a C-like language also encoded in F star called low star, and that language, both of these are supported by the F star type system to show that each of those artifacts refines the pseudocode. And so here's an example of, let me see, that was Veil, and here's an example, I don't expect you to read it, of low star. For each of those then artifacts, there is a compiler. In the case of Veil, it's really more of a printer that prints out assembly. And in the case of low star, there's a compiler written by Jonathan Pritsenko that emits C code. And that C code is actually quite readable. So all in all, there's about 8,000 lines of spec. There's about 100,000 lines of F star and Veil. That includes the proof automation. It's quite a substantial effort. And furthermore, here's one example of a particular curve implemented, and the CPU cycles here, lower is better. So you can see at the bottom here, Evercrypt targeted has the lowest cycle count. So they're doing the proof of the system, and they're also getting really excellent performance compared to handcrafted C and handcrafted assembly. So one of the ideas here is that proving programs also helps with performance. If you have verified your code at a higher level and refinement, you can do various optimizations and as long as you prove correct, those refinements are then shown correct, and so you can do more and more optimizations while retaining correctness. Whereas doing things by hand, every time you want to do an optimization, you potentially compromise the correctness. There's also a whole interop layer for interoperation between assembly language and C. So there's been a lot done on Everest. I'll just show you at the bottom the papers, at the top some of the deployments starting in 2016. There was a deployment in Firefox. WinQuick and the Tezos blockchain used Evercrypt in 2018, and in 2019 there's been more deployments of the code into Azure and into the Mirage OS. So the code is real, it's out there, it's on GitHub, and there's a whole community there that's really looking to this day where all our code at these low levels of cryptographic providers is really verified by default, because we've existed for too long with code that's substandard. Okay, very quickly, I want to sum up with the Ivy language and talk about language restrictions for desirability. And this is work done by Ken McMillan with his colleagues primarily at Tel Aviv University. So when we're doing all this automation with F star or any proof that's of interest and of scale, there's a lot of instability often when you're using something like Z3. And if you look at the quotes from this paper on using verification by Parno and colleagues, they talk a lot about this problem of instability. You change something in your proof, and the theorem prover goes off and just doesn't terminate. Timeouts are challenging to debug because you don't get a really good explanation. And then even once fixed, you make a really minor change and the proof will time out again. And also seemingly unrelated proofs might even time out. So there's a lot of unpredictability. So really, while I was singing the praises of SMT, the reality is when you're encoding and sending things off to this black box called the solver, things may not go so well. And primarily that's when you're getting into undecidable fragments. And so for most interesting properties, you're going to need quantifiers in your proofs about systems. So in every epoch, there exists a leader process. That's going to be translated into some quantified fact. And for Z3 in any SMT solver, quantifiers are a big problem. So here's a small example. For all x, f of x is greater than x plus 1, where you trigger on f of x. Well, when you instantiate this, you can generate an infinite sequence of instantiations, as shown below. And so if you're not programming with SMT carefully, your theorem prover goes and you get a space out or timeout. And getting the interactions of these triggers with your proof is very delicate. So what Ken has thought about deeply over the last few years is how to really structure programs so that proving becomes more predictable, more stable, and transparent. So by predictability, we mean when we reduce things to lemmas, we get, the automation works in a predictable way. And then if we make minor changes, like changing the name of a variable, or swapping two things where we have a commutativity property, we don't have a great impact on solver performance. And then when the solver does fail, it gives us an explanation, like a type checker does, that we say, hey, oh yeah, I understand, I'm writing something bad. So Ivy, the idea of Ivy that Ken has is to make maximal productive use of an SMT solver. The idea is these three properties of predictability, stability, and transparency will bring us productivity. How do we get these three properties? Well, we would get them by restricting ourselves to decidable logics.
We've got a few minutes left.
How many minutes, to be precise?
Like 3.
3? Okay. And then using programming languages and strategies to get the decidability. So Ivy is a new language that's a very interesting language for manipulating first-order structures with imperative programs. It supports theories and modular reasoning, and it supports decidable fragments transparently. So here's just a quick example of a classic sort of reverse copy function done with a traditional sort of inductive invariant that mixes both quantifiers and linear integer arithmetic. And for many proofs of this sort, when you mix arithmetic with first order, if you're not careful, the solver will perhaps go off the deep end and not return. So in Ivy, this code is not allowed because it's mixing two theories. It's mixing quantifiers and linear integer arithmetic. And so it identifies those. And Ivy, you're required to actually separate the reasoning. And so there's more work to do to essentially hide the linear integer arithmetic inside a module that can be used to explain essentially what reversal means. And I'm not going to go into the detail on that because I don't have time, but fundamentally the idea is that you can delegate arithmetic reasoning to a submodule that essentially encodes the meaning of reverse. And once you have this, you have a much more predictable decomposition of your verification condition. And so this isn't just good for toys, it's been done on Paxos and Raft. Ken and colleagues compared against Verity and Iron Fleet implementations of Raft and multi-Paxos. The proof to lines of code ratio was very reasonable, under 1 line of proof per line of code. And the checking was much more reasonable. So for Iron Fleet, for checking multi-Paxos, took 6 hours. For Ivy, a few minutes on a laptop. Reliable, fully automated, reliable counterexamples. So the lesson here is that if you're willing to restrict your language and do more careful decomposition, you can get the benefits of Z3 where you're restricted to decidable logics. And there's a set of resources there. So today I've shown you really a whirlwind tour from Boolean programs, propositional, to SMT encoded in F star, and Ivy doing restrictions. So all these languages have been used now for well over a decade at Microsoft. They're all open source, and there's more to come, but that's for another time. Higher order dependent types with Lean, and creating languages that are proved correct as well. So thank you very much. Any questions? We do have time. It's 11:20. I think we have time, right?
Yeah, we have 5 minutes.
Okay, great.
Hello. So you mentioned that the implementation in F star in the end is compiled to C. Correct?
Yes, that's correct.
So
well, it also some other backends as well.
So what about the guarantees of this compilation phase? Is this a verified compilation?
No, Kremlin is not yet verified. There's a project to do that, but the compiler Kremlin is not verified.
Okay, so is this being worked on, and do you?
Yeah, that's an active project. Yes.
Okay.
Any other questions? Phil.
How do these relate? So it was a great talk. It was really nice for a whirlwind tour. So you talked a bit about Everest and a bit about the Ivy project. The Ivy numbers looked really good in terms of the reduction in code size. How much of what Everest is tackling could be, in principle, done by Ivy if it grew?
Well, that's interesting. I mean, Ivy right now, its specification language is not as rich as Everest, and it's been focused primarily on protocols. So I think for the higher levels, like TLS and Quick, Ivy could be productively used as a domain-specific language for the protocols. For the lower levels, the crypto, I'm really not sure you would get a huge benefit in Ivy, but that remains to be seen. Certainly, F star is just much more mature in terms of the logics, and Ivy has a number of restrictions that might make it harder for it to do some of the crypto.
Right, but it was very different. Like for Ivy, it was less than one line of proof per line of code. But for F star, it's like order of magnitude more, right?
Well, again, these are sort of apples and oranges. So we were looking at the crypto versus protocols. So, I mean, one is very math intensive, and the other is more about state machines and asynchrony. So I don't really know how to compare this.
We probably have time for about one more question.
Thank you. That was a very interesting talk. I was wondering if you've looked at the usability. So there's separation of concerns there between your domain experts, say, specifying things in F star to the cryptography, and linking that together with things like ProVerif and CryptoVerif, which is a more domain-specific languages. As just to reiterate, so have you looked at the usability aspects of saying, here's this really cool tools that, say, programmers are developing, and the actual usability by the domain experts who need to use them?
Sure, yeah. I mean, the question I think is about usability, and that's been a big part of the tool chain is to make the error messages better, to integrate with IDE, to have IntelliSense, and also to recognize there are different domains and have DSLs for certain parts. So for example, for Everparse, there's actually a very high-level DSL for specifying grammars and a whole compilation chain there where you don't write inductive invariants at all, you just write in the DSL. So I think there's multiple aspects to that question, but still it is the case that primarily the authors of the crypto are very familiar with the tools, and over time we're looking to create DSLs and make the tools easier. That's still a work in progress.
All right, we have 1 minute, so we can do something quick, and we have a little flexibility as well. So any last questions?
Okay, thanks again.